Whatever. Okay, hello. I'm Chris Landauer. I'm from the Aerospace Corporation. Oh, it's on. I'm just not close enough. And I want to emphasize that what I'm talking about is my opinion because it almost never matches the official opinion of the company. My version of this is that it's high time we start instrumenting our flight software the way we instrument the flight hardware. Now, the polite version is I recommend that we start doing that. I've been very pleased so far at this meeting to hear a number of people who are beginning to do that. What I'm going to talk about is a little bit about what I mean by software telemetry, which may or may not match anyone else's idea, what you can do, how you can do it, some of the kinds of analyses that we can do, and then a little bit of conclusion. But basically, we need to measure the performance aspects of the software. As the software causes more and more difficulties, it would be very useful for us to know when that's going to happen in advance. Now, the issue, of course, is that software is really different. I'm going to talk about what I think needs to be measured, how you can report them usefully, what sorts of anomalies you can detect, because software tends not to break gradually. Software problems. These are two well-known issues that were caused by software failures. In one case, this was code that had flown for many missions already. So if someone tells you their code is good because it's already flown, do not believe them. The problem was that this code was reused, same hardware, same software, but a different operational environment. And anytime you're going to try to reuse any code, you need to be very careful about that operational environment. Similarly, another one, manual input. I mean, we don't do that anymore, but that was a surprise when I first learned of it. But, okay, telemetry is about hardware health and status. Historically, that's what we've been doing for a very long time. Now, the problem is, if we're going to try to do this with software, we have to notice one important feature of software. Software is not subject to the laws of physics, the way hardware is. That means that the number of kinds of things it can do badly is much, much larger. So I will say in one sense, software is much more complicated than hardware is. But that's because I'm a software guy and I don't know anything about hardware. Software does not change gradually. In complex systems, sometimes you get this notion of bit rot, where you have systems that are gradually going out of whack. But the size of systems we have in our software makes that a little bit less likely. We have, I'll say well-defined functions, which is usually the case. I'll say usually it's relatively small software compared to some of the kinds of ground systems that we've seen. But the idea is that software does not break gradually. It's either broken or it's not. And sometimes that happens because it's being used in a way that's unexpected. And sometimes it happens because we just kind of didn't get around to fixing that part. What can we learn? We know, as we build the software, especially the applications that I've heard at this conference about people who are using certain kinds of model-based software development, we know what that software is supposed to be doing. And very often it does that. It would be very useful to be able to track that. You know, when you write a piece of code through a model or otherwise, you know where the edges, where the squidgy parts are. And being able to test that on the fly would be really, really useful. Because first of all, you can learn something like, this code is not being used exactly the way I thought it would be. There's something else going on here because of the interaction with all the other system components. Knowing something about that would be extremely useful. Now, the other piece is that because the software behaves differently, you have the opportunity to measure much longer time periods, much longer sequences of information. You know, if hardware is going to break, it's usually we're testing thresholds, we're testing periodicities, we're testing a few kinds of parameters, and the mathematical analysis required tends to be fairly simple because the hardware tends not to repair itself. But now we can start looking at the kinds of anomalies. We expect this system to behave in such a way, but it doesn't, so let's find out why. We are assuming that the behavior of this software matches the model we have, Well, that's something we can check on the ground at least. And sometimes you'll end up with, as you write a piece of code, oh, I've set this variable to that variable, I know what this value is. Except that because hardware wears out over time, that may not always be the case. So every once in a while, checking that an assignment actually worked could be very useful. What needs to be measured? Well, if I have a piece of software that's running, I want to know certain things. I want to know, for example, how often is this module called? gprof is a particular Unix tool that does a profile for systems that tells you for some very fine-grained slices through the code address space how many times you went through that piece of address, how often functions were called. There's a whole series of useful things you can learn about a program. You can learn where bottlenecks are. You can learn where things that you thought would be used that don't get used. Statistics of the decisions. We heard a couple of talks today where knowing all the branch points and checking all the branch points isn't enough because they interact. And it was checking the number of paths through the system. There were paths through the system that, different paths, same branch points, that caused errors. We saw an example of that a couple of days ago. How long for straight segments? This software is supposed to be doing something. So it would be very useful to know how long some of these efforts are taking. As we get farther and farther away from direct programming of the basic hardware, we're starting to get into cache issues. We're starting to get into, if I have a little database and I access that database, does it take the same amount of time every time? The answer is almost certainly not, because we have a whole bunch of other things that are helping us. We're from the software. We're here to help. Schedule margins. If I'm running a hard real-time system, I want to make sure that the schedule margins stay high. If, as usually the case, we're kind of crammed all these tasks into the program, we're going to have some issues of running up against the edge of the schedule. It'd be nice to know that in advance. If it's because, for example, a database is filling up or you're getting collisions and certain kinds of computation, we can usually see that early if we're looking. All the values, buffer fill values. Buffers fill up, that's kind of what they do. There's a whole series of other kinds of measurements one can consider, and obviously I'm not going to try to even start to say all of them. What will happen, I hope, is that over the course of the next while, people will try this out. They'll try out measuring the software behavior. They'll learn what's important. They'll learn what's perhaps important, but that just doesn't go wrong very often. They'll learn what we don't need to do, which is always a useful thing to have. And now, how can you report? Here's a case where, because the software behavior is so less constrained than hardware, we're going to want to have some very different kinds of reporting mechanisms. So I'll talk about a wide field display. Imagine a map of your code, and you have just a density plot. How often does this piece of code get called? You could predict what that's supposed to be from your models. And if it doesn't match, then something weird is happening. Very often it's because the hardware models that were used to verify the software behavior aren't exactly right. That has happened to me, well, every time. But you can go and compare the behavior of the model with this and just a picture. And you watch this picture and you start seeing things that light up in different colors. Maybe you have the two density plots, maybe you have a difference in the density that shows up in a certain way, and that pinpoints where the code is not behaving the way you expected it to. Useful, I think, or would be to me. We had a system a long time ago that had a transistor radio wired to 1 bit, and you could hear your programs run. This was a 7094. So you knew it was only running one thing at a time, but it meant you could hear your program, and we could tell just by listening whether the program was doing the right thing or not. We're really good at that. So in this case, you have a lot more complexity, a lot more things going on at the same time, but a picture of a code density plot seems like it would be quite useful. Multiple summaries, long-time displays. You want long-term displays because you have, in any kind of orbit, you're going to have some periodicities in behavior. You're going to have some occasional behavior. You're going to have some interactions between different kinds of periodicities. There are ways to tease out those differences and have a look at them. Those would be quite useful to do. Buffer fill schedules, I talked about that already. Fault management. There is code that you don't ever want to have execute. and that's the fault management system, except it will. So one of the things that you have to watch out for is to make sure that the behavior of the fault management process is as you expect. And again, from your original models that you use to generate your code, you can produce an appropriate sort of code density map for what happens for certain kinds of faults. And you can do the same kind of code picture as others. What kinds of anomalies can occur? I got in trouble for this one for calling unused code an anomaly. I mean, if it's unused, why did you write it in the first place? But the issue is for certain kinds of code, you know, safe holding code, you don't want it to execute very often. But in particular, every program I've ever worked on has had not just unused code, but unusable code. It was there when the system was at one stage of its development, and instead of taking it out, it was disabled. You can't disable code because sooner or later something's going to happen. Somebody's going to say, well, let's try this. Or you're going to get a single event upset that jiggers your address register or something. Unusable code should be unusable in a really strong sense. Now, one of the reasons for not taking out code that's already there is to make sure that your address space, the addresses of what you have, don't change. But you can do that by zeroing out the code you're not supposed to use. Just make it empty. Then it can't do anything bad. You get an illegal instruction trap and go out and say, there's no reason I should have been executing that instruction. That's a bad thing. Buffer overflows. Very often in some of these cases, we had large swaths of code that were unused because they were in there for original testing or something. But they weren't actually tested themselves. You know, testing your test procedures. We heard several about that. Hardware faults. Hardware faults will happen, transient or otherwise. These things do happen, and one of the hardest parts of writing code is writing code when you can't quite trust the hardware. And we've had a number of cases where a hardware fault was exacerbated by the software because it was thinking something else, and it made the problem substantially worse. Software assertions. There's a long history of assertions, using assertions in software to check certain values internally. But in many of these flight software systems, we're trying to squeeze out the last little bit of performance, and we don't want to have the system checking a bunch of assertions all the time. That should properly be the ground station, the ground systems. We've got more time there. Lots and lots of other kinds of anomalies. Function inputs out of bounds. That filter issue was an issue of having a data smoothing filter with a coefficient that was wildly wrong, which could have been known in advance, but it wasn't. Lost the satellite because of that. What can the ground systems do? This is the part that I like. I'm a mathematician. I like numbers. Lots of numbers. All the data that you're going to get, this is also true for hardware, is going to write timestamp sequences of one kind or another. Now, one of the things that you can do is that there's a large number of, I'll say new, they're relatively new mathematical methods for dealing with long sequences of numbers. It's dealing with these trajectories. I'll come back to those in a minute. There are some things that we already know. We do this all the time. The Kalman filters, various limit bounds checking, trend checking. If your system is, some measurand is gradually moving towards a boundary, that's a cause for a certain amount of worry. Having the long-term behavioral models of the telemetry is also a really useful thing to have. You know, you see people who have been operating systems for a long time, and they go, yeah, it does that every once in a while, and then it stops. So it's okay. That's normal. Except developing that kind of long-term model is really difficult because, you know, we have missions that last months and years, and you don't test something that long typically. You know, I mean, just think of the response you'd get if you say, okay, well, I have a 10-year test program. Periodicities, accumulation points. There's a whole bunch of very interesting new mathematical methods. One of the things that I like to do is what I call grammatical inference. It's a classic technique in language processing or programming language processing. But what you're looking for there is recurrent patterns of events. And this could be exceeding a threshold. This could be value sitting in a certain interval. What you're trying to do is build models of the actual behavior of the system so you can compare them to your original models of your intended behavior. Those are extremely useful kinds of things to do. and a couple of more. If you think about a trajectory for any measured value in a system, that is a point in a very high dimensional space. There's a whole series of new kinds of mathematical methods, where in some cases the mathematics is less than 10 years old, and that's yesterday for math, called manifold discovery. Suppose we can show that those trajectories always live in a tiny little subspace of the total set of possibilities. What that tells me is I have just learned new constraints on the values that occur. What that tells me is that I now know some things about that behavior that I did not know before. And that can be extremely useful for planning, for measuring, for also checking that the system is continuing to follow within those spaces. This is new stuff. Manifold discovery, dimension reduction. This is a way of discovering what I'll call operational constraints, because they are constraints on the behavior of the system as it is doing whatever it does. And then what you can do is you can set up new tests to see when you're coming close to violating those constraints, or when you're violating them more than some threshold or other. But the idea is that there's a serious amount of analysis that can be done in the long term to help you with the software and the hardware. So far we haven't really needed it for hardware, but I don't think it's a bad idea to try it. It's high time that we do this, or at least start to do this, start to do some experiments. We have lots of models of space systems. Let's watch them. Let's run them for a month, see what happens. Let's see if we can develop some of these behavioral models of long-term behavior of these systems, given that it's always the case that if it's a piece of hardware, it's gradually degrading. It would be really useful to be able to detect that, both in the software and the hardware, because you might want to change the software. You know, if all of a sudden some piece of your hardware is not doing exactly up to its full performance, then you might want to change some of the behavior, some of the ways you're using it. Flight software should happen in the real time. It should happen in the operating system. It should be done everywhere, just like we try to do it everywhere for hardware. Of course, we will eventually learn which ones we don't really need to do. That, I don't know. I don't think we have done enough experimentation to know that now. We can't decide a priori what we don't need to test. Because you know every time you decide a priori what you don't need to test, you know it's going to happen. Lots of different methods. There are lots of interesting new mathematical methods for the analyses. There's lots of long history in software development of, I'll say automatic testing, but ways of learning something about the way your code is behaving. I think those things should be done for spacecraft. I think those things should be done for flight software, and I think those things should be done now. Thank you.